Hello, in this lecture, we are going to continue with the series on the revisit of wave mechanics. Today's topic, we are going to discuss more about probability current density. Although we have done this topic in greater detail, but still a few points I felt were missing and which needed a separate lecture. And in this lecture, we are going to do most possibly the questions also. And we are going to uh, write down some very important results as well. So without wasting time, let us start. Okay. So previously we've already done that the probability remains conserved globally. Okay. So probability remains conserved globally. Now there is an equivalent statement um, with like local conservation probability. Okay. Local conservation of probability. That is, let's say I already know that probability, I'm writing it here, probability, this probability, it is a conserved quantity. It is a conserved quantity. Okay. That is, if I calculate probability of finding the particle anywhere in the space, which is given by mod psi square dx, then it should be a constant, and that is 1. Okay. As the time passes, with the change of time, wave function changes. And so does your psi mod whole square. Okay. Now, in a localized volume, if the probability is increasing, then it must be decreasing somewhere, because in total probability should remain conserved. So if probability is increasing in a given volume, then it must decrease in some other volume. So an increase in probability in a localized volume must be accompanied by an equivalent decrease in some other region. Okay, so this is point number 1. So it seems that probability flows like a fluid. Okay, so there is a continuous, you can say, sort of uh, current-like behavior for the probability. Okay, this is one thing. Now, there's an important equation which is called as equation of continuity. Just I'm giving you an idea. What is equation of continuity? Let us take the example of fluid. This equation of continuity also exists in the electromagnetism also, but just let us take an example of fluid where you have a surface S which bounds the volume tau. Let us consider a point P, and there is a patch of area which is, let's say, dA. Let J vector represent the mass density. If you want to find total flux of fluid passing through this entire surface, it can be written as J vector dot TA to the surfaces. Now, if some mass is coming out of this localized volume, since the total mass should remain conserved, so there must be decrease of mass in this volume. It must, this particular outward going flux of mass or outward going flux of the fluid must be accompanied by the decrease of mass in this volume. So I can write this should be equals to minus of dm upon dt. In other words, I can also write this as minus of d by dt of integration of rho d tau. So sorry. Also, I can write this as, I know from Gauss-Divergence theorem, I can change the surface integral into volume integral. Since this volume is arbitrary, we can take any volume, not only this, we can take any volume. So overall, we get that del rho upon del t plus del dot j vector d tau is equal to 0, which implies what? It implies that del dot j vector plus del rho upon del t is equal to 0. This is famously known as equation of continuity. This is famously known as equation of continuity. And we'll see that while working, we've already seen that while working with the probability density, the time rate change of probability density, we're going to see this same equation appearing, almost similar structure. Now let us consider the case of probability density. Okay, let us consider the case of probability density. We know that the probability of finding the particle can be shown to work like a fluid, okay, which can flow. There, and also it is a conserved quantity. And we'll find that this probability of finding the particle somehow satisfies equation of continuity along with the proper definition of J vector. So here J vector would be not only mass density or current density like in electromagnetism or fluid mechanics. Here J vector will be called as the probability current or probability current density. So let us see how it works. So let us consider that rho is equal to psi mod whole square, which is indeed equals to psi star psi. And if I know that iota h ket del psi upon del t, it is equals to minus h ket square upon twice m psi plus v psi. So I can write this as h ket psi simply, and this is iota h ket del psi upon del t. And from here I know that del psi upon del t is equals to 1 upon iota h ket, and this is like Hamiltonian being operator on psi. Now this is one thing. Now if I want to calculate what is del rho upon del t, it is equals to del psi star del t, and then you have the psi plus psi star into del psi upon del t. Now instead of this, I'll place this. So I'll get del rho upon del t is equals to 1 up, sorry, this is star, so I'll get minus 1 upon iota h. I'll get h ket psi, and I'll write h ket psi, which is equivalent to what? So sorry about it. Okay. So it is equals to minus of h ket square upon twice m del square psi star upon del x square plus v psi, v star psi, and again psi. And then again you have this 1 upon iota h ket And then you have this psi star. And again you have this thing minus of hk square upon twice m del square psi upon del x square plus v psi. So overall, I know this del rho upon del t is equals to what? It is equals to h cat upon 2 iota m, h cat upon 2 iota m negative. You have this psi star del square psi upon del x square minus psi del square psi star upon del x square. This psi star is like taking conjugate, okay? So overall, I come to understand that this particular quantity, I write it as minus of del by del x of h cat, and this 2 iota I'll place inside. So this is m, and instead of this, I will write this is imaginary part of psi star del psi upon del x. Just think about it. If I place this 2 iota inside, so this is imaginary part of this particular entity, because after all, what is imaginary part of z? Z minus z star divided by 2 iota. This is how I write. Okay, so this is one point. Just understand that this is called as your probability current or probability current density. And this equation, you can just think what it is. It appears like equation of continuity in one dimension. So clearly, your probability density satisfies the equation of continuity with the proper definition of J vector here. In this context, the J vector is called as the probability current density given by h cat upon m, an imaginary part of psi star del psi upon del x. Okay. Okay. And now just let us think about the dimensions. We have already discussed about dimension, but still, just let us revise the dimensions. What would be the what do you think would be the dimensions of J vector or Gx? Okay. So for that, I'll do one thing. I will try to use the notation del t is simply equals to del by del t, so that time and again I don't have to write the same. And if I'm writing del by del x, it will be simply del x like this. So basically, this equation I can write in this fashion. Um, Now, what I'll do, I'll try to integrate this from x0 to x1. I'll try to integrate this from x0 to x1. So this is like del t integration x0 to x1. Just remember, this is rho dx plus del j upon del x times dx integration from x0 to x1. So what do I get? I simply get that del by del t of this. What is this? This is probability of finding the particle from x0 to x. Just remember, this rho is psi mod whole square. Psi mod whole square dx is probability of finding the particle from x0 to x1. So this is del by del t of simply your probability, right? And it is equals to minus of j of, or you can say j of x0 minus j of x. Just an idea. So this is like d by dt of probability. And here you have this j of x0 minus j of x1. Clearly, you can see that probability is a conserved quantity. Okay, this is a quantity which is some constant. So overall, you can see that j is inversely dependent on time. So you can just have an idea from here itself that the dimensions of j in one dimension, that is probability current in one dimension, will be an inverse dimension to that of time. So basically, it will have inverse dimension to that of time. In SI units, I will write second inverse. Okay, this is one thing. Just an idea I'm giving you how to just assess it. Okay. Now, if I just write it in 3 dimension, so also this particular equation must work in the 3 dimension. So if there is a rise of probability in a given volume, so let's say if there is an influx of probability current density, so there would be some rise of probability in this region. The rise of probability in this region must be accompanied by a decrease of probability in some other region. Or you can say that rise of probabilities in this region must be because of the incoming flux of J vector. Okay. So I know that also in 3 dimension we can understand it like this. So in 3 dimensions, the rate of increase of probability in a volume, let's say omega, let's say the volume is omega and it is surrounded by a surface d omega. In a volume, omega must be equal to the inward flux of probability must be equal to inward flux of probability across the surface. Let's say here we have taken across the surface d omega um, that bounds the volume omega. Okay, and here the probability will be given by psi star r vector comma t times psi. Okay, and what is j vector here? So j vector here is h cat upon m, imaginary part of psi star grad psi. And we already know that this is equivalent to writing okay plus del dot j vector theta, or in terms of surface integral, we can write the same as this. And these are all mathematical manipulations. Okay, much of physics is lost here, and I'll let you know what I mean when I say it. Because see, flux is one of the terminologies which you can use in classical physics, not that way in quantum mechanics. But I'll come to that point. Okay. Now just understand that overall, one can expect that this entire entity must have dimensions of inverse of t. This must have dimensions of inverse of t. Yes or no? Because see, this is dimensionless and this is 1 upon t. So this must have inverse dimensions of t. But already you know that j is getting integrated with ds. So if at all overall this integral must have an inverse dimension of t, then j in general must have the dimension of, because this is ds, the ds dimensions will be what? This will be dimensions of meter square. So obviously j must have some dimension inverse of m square also. So it should have dimension of m minus 2. And I know that overall this integral has dimension of inverse of time. So this way. So in 3 dimension, if I'm talking, then the probability density has a dimension of m minus 2, s minus 1, or you can say in terms of length and time, this is our. Okay, so understand that is why we say probability current density also at times, because it's just not probability current, that is, it is just not flow with respect to time. It may be divided by some area element also, depending upon the dimensions you are talking of. So for example, in 1 dimension, it is flow of probability per unit time. So it is 1 upon t. But in 3 dimension, it is the flow of probability per unit time per unit area. So basically here you will have to use the term probability current density. So therefore, at times you'll find many books writing it as probability current and many books writing it as probability current density. Why probability current density? Because you see, in 3 dimensions, you can understand it is like probability flowing per unit area per unit time. Like this is m minus 2 means per unit area per unit time. So from a cross section, if we are talking, so per unit cross sectional area divided by per unit time. Current, like the probability flow. So this is how you can say that this is current density, probability current density. So probability current density, why? Because there is also division of some area element. So this is the dimensions of J vector, or you can say dimensions of J in 3 dimensions. Okay, this is one thing. Okay, now let us move to some important, you can say, results that I'm going to list. See, one more important topic, just consider the beam of particles. Okay, let us consider something called as beam of particles. Let us say that the beam of particles are heading towards the x direction, and we are not considering any interaction among these particles. Further, we are just thinking that we are just taking that all these particles are moving with a uniform velocity v. I'm giving you just an idea, okay? Just an idea. So let us consider a cross section A here and consider a cross section B here. And the particles are moving towards the right direction, towards the right. Particles are moving towards the right direction. Okay. Now, in time dt, let's say in time dt, if the velocity is v, total distance traveled would be v dt. Okay. So let us say that number of particles between AB would be what? Let's say n is equals to number of particles per unit length. And I already told you, let's say in time dt, total number of particles in this particular AB would be what? It would be v dt. Sorry, the length is v dt. So total number of particles would be what? Total number of particles would be n v dt. So all the particles which are contained in this particular section will be crossed from v only. Will be crossed from v only. So in dt second, total number of particles crossing the cross section B would be what? Would be equals to nv dt. Okay. And as we've known that if I want to calculate the flux, here flux would mean what? Total number of particles per unit time. So total number of particles per unit time, you can say total number of particles passing B per unit time. So per unit time means again divided by dt. So flux would be equals to n times V. So this is your flux of B. Now also understand what is probability density. So probability density is psi mod whole square is the probability of finding the particle in some range, right? In some range, let's say in d tau or in x to x plus dx. If I'm doing like if I want to write into dx, so this represents the probability of finding the particle in some range. and otherwise it is probability density, means this is probability divided by some length element. So in general, the psi mod whole square can be thought, or is proportional to the number of particles per unit length. Okay, so basically, what is probability density? Density means probability per unit something. So it may be per unit time, it may be per unit length, it may be per unit volume also. So I know that, probability per unit time, per unit length, or per unit volume. Let's say in 3 dimension, it is probability per unit volume. So therefore, whenever we have to calculate the probability, we do the psi mod whole square d tau. This is probability in 3 dimensions. So basically, probability density here, the dimensions would be total number, like probability of finding the particle per unit volume here. So basically, if I'm talking of in 1 dimension, then psi mod whole square would be proportional to total number of particles per unit length. Is that clear? Okay. Now let us try to understand this using an example. What I want to suggest. Okay. So let us consider an example. So I'll take an easy example. So this is like psi as a function of x and t is given by a e की power iota upon h cat, and then you have this px minus et. We want to calculate the probability current density, and we want to check that what is that relation with the flux of beam. What is that relation with the flux of beam? Basically, this is an equation of particles moving along the x-axis, positive x-axis. Is that clear? Now, I have already told you that what is J? J is equals to h cat upon m, imaginary part of psi star del psi upon del x. So I'll write this as h cat upon m, imaginary part of a star e की power minus iota upon h cat px plus iota upon h cat et times the derivative. So derivative would be iota p upon h cat, and again we'll have a e की power iota upon h cat px minus iota upon h cat et. So what I'll get? I'll simply get this equivalent to h cat upon m a mod whole square, imaginary part of iota p upon h cat, which is simply p upon h cat. So I'll get p upon m a modulus whole square. So this is J. Okay, if you remember this kx wave vector, right? If you remember, this p would be here momentum, because p in quantum mechanics can be written as h cat k, and only then this will be a wave vector here. So one thing is very much clear, that this represents some kind of momentum. So momentum divided by mass, this should give you some dimensions of velocity. So you can take it as some velocity thing. What is a mod whole square? If you just think slightly, a mod square would be simply psi mod whole square. And I told you what is psi mod whole square. Psi mod whole square would represent number of particles per unit length in 1 dimensions. So in 1 dimension, if I'm talking number of particles per unit length, because probability density would have dimensions of 1 upon something, like 1 upon length, 1 upon volume, something like that. And it represents probability of finding the particle per unit length. So basically, probability means what? Probability of what? Finding the particle. So total number of particles per unit length. So you can say that this A mod whole square would be proportional to total number of particles per unit length. So I have already given this as N. I already know that this is NB. So J is equals to what? J would be equals to NB. In 1 dimensions, if you remember, what did I say? NB dt would represent the probability of particle, NB dt would represent the total number of particles passing through B in time dt. And if I divide it by dt, I will get the flux. So flux of the beam passing through B is simply n into V. Similarly, here also you get something like n into V. So you can clearly see that this probability density probability current density, you can say that it is proportional to the flux of particles in the beam. It is equal to the flux of particles in the beam. Okay, so in summary, I can write here that if a beam of particle is represented by some wave function, then we understand that psi mod whole square can be interpreted can be interpreted as being proportional to the number of particles per unit length of the beam. And further, the probability current density which is J vector, simply J, then represents the flux of the particles in the beam. Okay, now let us do a few things. Let's consider a Gaussian wave packet. Okay, let us try to find the J. J is equals to h ket upon m, imaginary part of psi star del psi upon del x. I'm leaving this calculation for you. I have already done it in previous classes. So I'll get something like a mod whole square e raised to power minus of 2x square upon a square, and then I will simply get p naught upon m. So, and if I just think what would be probability density here? So probability density would be this entire thing. So this represents your probability density also. And p naught upon m can be taken as the velocity. So clearly you can see that J takes the form. So J takes the form for Gaussian wave packet as rho into V. So one of the important result is this, that for Gaussian wave packet, J can be written as rho times V, where rho is the probability density and V is the velocity of the wave packet, you can say. Or okay, and okay. Now this is one thing that you should remember. I think all these cases we have done previously also, but just to revise it for you, I'm doing, and we'll list some important results also that we may have missed while doing the topic initially. If I just take something like this, okay, so if I just take a simple case of, okay, so in 3 dimensions, let me take a plane wave now. Let me take a plane wave. And in 3 dimensions, I can say that my plane wave is simply equals to psi is some constant. Let's say, let me take it as e to power minus of, let me take something like, generally it is iota kx. So I'll write it here. Some minus iota upon h cat, and I'll write instead of p vector dot r vector. And let me also multiply a time factor. And you'll find that this time factor does not uh, change much of the things. So even if I'm writing it, even if I'm not writing this, okay. So basically, I can summarize it in this form that for a plane wave, I can write psi as a function of r vector and t as simply some constant c e to power of, so I'll write exponential instead, iota upon h cat p vector dot r vector minus et. Now, if I want to find the probability current density here, so probability current density can be written as h cat upon m imaginary part of psi star grad psi. And if I calculate this, I've already done it for you in previous lecture. It comes out to be equals to p vector upon m. So if I'm writing vectorially, it's p vector upon m times c mod whole square, which is again equals to velocity times psi mod whole square. So this is probability current density. Probability current density represents the number of particles passing per unit time. And because it is in 3 dimensions, so it also represents per unit area also, like per unit cross section also. So psi mod whole square, number of particles passing per unit time, per unit area into velocity, into velocity. So this entity is equal to what? J. And what is J? It is number of particles flowing per unit area per unit time. Okay, this is number of particles flowing per unit area per unit time. What is psi mod whole square? Psi mod whole square is number of particles per unit, uh, because it is 3 dimensions per unit volume. Here there would be meters per second, meters per second. So meter cancels meters per second is here. So basically it represents the number of particles passing per unit cross section per unit time. So if I just, okay, are you getting my point? So this is what I'm just writing it as here. It is meters per second. Okay, this is kind of meters per second, and this is kind of something divided by volume sort of. So you'll get this meters cancel meters, so you'll have meter square. So overall, this entity will have dimensions of meter square second inverse. What does it imply? It implies that this entity is number of particles passing a cross section. Let's say this is your cross section. Number of particles passing across section per unit area per unit time. This is your probability current density, or at times known as probability flux also. So it is probability current density here. Or at times, this is called as probability flux also. Okay, but But understand that this kind of interpretation is suggestive, no doubt. Okay. So one important note I'm making here. That although uh, this interpretation is just suggestive, it must be realized, it must be realized that J vector is not susceptible to direct measurement, is 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 not susceptible to direct measurement in the sense, you can say, in the sense in which the probability is. Okay, because it would be misleading if I'm saying that it is susceptible to direct measurement. Why? So I think it would be why? Because if I say that this J vector somehow represent, if J vector T somehow represent averaged uh, measure particle flux at, let's say, R vector n time T, then the measurement of this local flux then measurement of this local flux would imply simultaneous measure of, I'll write here, would imply simultaneous high precision measurements of what you can say position. I'll write it here. I'll write position only. Position and velocity. Position and velocity. Okay, like velocity means here, or you can take like momentum also. Position of momentum, and which is inconsistent with the uncertainty principle. Although still at times we will take this idea of flux only, uh, especially when it is not that dependent upon r vector. Okay, so understand that it is sometimes very helpful to think J vector as a flux vector, especially when it does not depend or only slightly depend upon R vector. So if that is the case, then we will take this J vector as a, you can say, we can interpret that as flux. So therefore, you've seen quite many times that while I was doing this, I was not actually doing some physical thing. I'm just trying to compare what the units are suggesting. So basically, it is suggestive. The interpretation of flux is suggestive. However, saying flux of probability current may be a little bit misleading. So understand that, okay, somehow it fits into our equations, it fits into our understanding that way. But overall, uh, this may lead to a assertion that if I'm saying that J vector is an average measured flux, particle flux at R vector and T, it would imply a measurement of this local flux in local flux that is simultaneous high precision measurement of position velocity, and which certainly is not very uh, in line with the quantum mechanics. So just giving you a note a little bit so that don't get trapped into this. But overall, it would be, I'll write it here. It would be certainly beneficial, or certainly useful to interpret J vector as flux or probability flux also, especially when you can say that when it depends on R vector slightly or not at all. So in that case, one can make accurate velocity measurement. Okay, so accurate velocity determination can be done without impairing the use concept of usefulness of concept of flux. So I hope I have been able to put my message forward. But if you're not getting it, please let me know in the comment section. Okay. Now, one more important result uh, that is worth stating here. I'll write it here itself. That if you have superposition of two plane waves, let us say, I'll take for example, I'll take if you have superposition of two plane waves instead of one plane wave. So now I'll not use 3 dimensions, I'll simply use 1 dimension. Let me say that it is e to the power iota kx, and let's say another one is b e to the power minus iota kx. If we want to find, you can say the j for these superposition of waves, we have already calculated this. This is equals to h ket k upon m times mod of a square minus mod of b square. Okay, so if there is a superposition of plane waves, then j vector along x-axis, for example, if I want to write it along x-axis, then j vector along x-axis is given by h ket k upon m mod of a square minus mod of b square. And remember, if I'm talking of j vector, it is equals to the flux of beam. So it is equals to the flux of beam. Flux of beam. And how can you write flux of beam? It is written as n into v. N is number of particles per unit length. Okay, this is per unit length. Per unit length into velocity. So I can write my j in 1 dimension is directly proportional to n into v. Okay, so here h ket k represents p upon m. So p upon m is simply velocity times number of particles uh, per unit length, number of particle per passing per unit length. So I hope I am able to somehow make you understand. Let me just take one more example to make you further understand this. So let's say I have some two separate beams of, let me take two separate beams of particles, and they are described by wave function psi1 given by a1 e की power iota k1x and psi2 is equals to a2 e की power iota k2x. We want to calculate the ratio of flux of particles in the first beam divided by flux of particles in the second beam. I already taught you that probability current density is directly proportional to flux, and which is equals to n into v. N is number of particles per unit length, and I know that this is you can say that number of particles per unit length. So your A mod whole square, that is the probability current density. The probability density is directly proportional to the number of particles per unit length. So basically, if I'm writing for first one, so if I'm writing J1 upon J2, it will be equals to mod of A square into V. V here would be simply K1 divided by mod of A2 square, sorry, K1 square into K2. So it is equals to K1 mod of A1 square divided by K2 mod of A2 square. So this is how you do it. Okay, so let's say another question. So for example, I gave you this mod of A square minus, so this is superposition when you have the superposition of plane waves. So it represents what? It represents something like velocity here. And it represents the number of particles passing along x-axis. Per unit length also, number of particles per unit length passing along the x-axis. I hope it is clear. Okay, so now just let me do another example so that you will be able to understand what I want to convey. So let me take one more example just for this plane, superposition of two plane waves. So let's say I have a wave function described by a e की power iota kx plus e की power of 4 e की power minus iota kx. So I think this should be, I'm not writing a then. Okay. This is how it is. We want to find what is the total probability current density. We want to find total probability current density. So as you're aware, the total probability current density would be equal to what? H ket k upon m times a mod whole square is simply 1 minus b mod whole square is 4 ka square is 16. So this will be minus 15 mod a square. Just take some a here so that mod a square h ket k upon m. And if someone says that what would be the ratio of particles going through x-axis divided by particles going through negative x-axis, then what the answer would be? Simply you can see that along the negative x-axis you have this 4. So basically it would be proportional to some J1 upon J2, or you can say, it is equals to J1 upon J2, and J1 is proportional to K1 A1 mod whole square upon K2 A2 mod whole square. In both of the cases, K1 and K2 are same, so it is equals to mod of A1 square upon mod of A2 square, and it is simply equals to 1 over 16 for that matter. Okay, we've already done the case of the spherical wave. For spherical wave, I'm just writing the result. We've done it previously. Please see that. For spherical wave, the wave function can be written as a upon r e to the power iota kr. And here the expression of probability current density turns out to be a mod whole square h cat k upon m, and then this is 1 upon r square. From here also you can see this is 1 upon r square, h cat k upon m. This will be the dimensions of, this will have dimensions of velocity. This will have dimension of 1 upon r square, that is 1 upon meter square. And this will have uh, dimensions of velocity. So here you can say that number of particles per length per time. Okay. So I hope all these cases we have done previously also, just giving you a hint of, making you revise these concepts. Okay, one more important concept that you should remember is that if I want to find the integration of this gx dx, okay, if I want to find an integration for this gx dx for any normalized wave function or wave packet, you can say right now, wave function in one dimension, then it comes out to be equivalent to averaged value of px upon m, or simply it is equal to the expectation value of px divided by m. This is again an important result. This is an important result. See how? So just giving you a little bit of hint. So what would be j? I know j is equal to what? Minus infinity to plus infinity. I'll simply write h cat upon 2 iota m. I'll write the entire expression. It is equals to psi star del psi upon del x minus psi del psi star dx. Okay, this is how it is. Now you just think this is equals to h cat upon 2 iota m, and here instead of writing del psi upon del x, what I'll do, I'll multiply iota h cat and I'll divide iota h cat. So, I'll multiply minus iota h cat and I'll divide 1 upon minus iota h cat. So I'll divide this way. This is minus infinite to plus infinite. This is psi star. Inside I'll get minus iota h cat del pi del x of psi dx. And this part is nothing but the complex conjugate of this part. So instead of writing this entire business, I'll simply write this as minus of complex conjugate of this. CC represents what? CC represents the complex conjugate of the first integral. Complex conjugate of the first integral. Okay, this is fine. So that it no longer we are bothered for it. So basically what we want to evaluate, we want to evaluate minus infinity to plus infinity gx dx. It is equals to h cat upon 2 iota m. Now just pay attention. This first bracket is nothing but it is the expectation value of px only, right? That is why I deliberately chose to multiply with minus iota h cat and divide by minus iota h cat. So this is simply px cap. So this is expectation value of px in the first bracket. So overall this is px divided by minus iota h cat, and this is a complex conjugate of this. So simply it would be equals to what? It will be minus px upon iota h, because minus iota complex conjugate will be simply iota. So overall I understand this is equals to h cat upon 2 iota m, and this is 2 px divided by iota h cat. And there is a negative sign as well. So this is negative sign. So overall I get to know that this h cat cancels, 2 cancels, this iota, so multiply iota, so you get an iota here. Not iota, sorry. This iota is here, iota is here. So iota square is -1. So minus minus plus. So you'll simply get Px expectation value divided by M. So this is an important result that you should remember, that if I take an integral of my from minus infinity to plus infinity gx dx, then I simply get the expectation value of Px divided by M. If you just remember, in expectation value, we've also done that the expectation value of Px for real wave function is 0. And this is quite apparent from this result also. See, if I want to calculate the current density for any real wave function, current density for any real wave function is always 0. Why it is 0? Because see, what is current density? Current density is simply h cat upon m, imaginary part of psi star del psi upon del x. Now, if psi belongs to, if psi is real, okay, if wave function is completely real, then this would be what? This would be real, this would be real. So the imaginary part, there's no imaginary part as such, so this would be 0. If this is 0, then this is 0, and if this is 0, then expectation value of Px is also 0. So always remember, the expectation value of real wave function is always 0. And also that if I want to find what would be the current density for a real wave function, it is also 0. So now let us discuss something regards additivity. Let us discuss something regarding additivity. Additivity of probability current density. To this end, I'm going to take a wave function which is superposition of two plane waves given by psi1 is equals to a1 e की power iota kx and psi2 is equals to a2 e की power of minus iota k1x. Okay, let us take the wave function to be superposition of two wave functions. Then we'll see that the corresponding to this, let us say the probability current density is J1. Corresponding to this, let us say the probability current density is J2. Then the total probability density can be written as J1 plus J2. You can say that the superposition or additivity also holds in terms of the probability current density. It can be shown this way. So if I use psi1 and psi2 is equals to psi, and if I want to find J is what? It is equals to psi star del psi upon del x whole imaginary part times h cat upon m. So let us try to find this. Let us try to find this bracket. So I'll list all these things. So basically, what is my psi1? My psi1 would be simply a1 e की power iota kx. What would be del psi1 upon del x? It would be simply iota k a1 e की power iota kx. Then what is del psi2 upon del x? It would be iota k a2 minus e की power minus iota kx. And then you have the psi2 simply equivalent to writing it as a2 e की power of minus of iota kx. And these a1 and a2 are real constants in plane wave. So if I want to calculate the current density, so current density will be equals to imaginary part of psi star del psi upon del x, which is equivalent to writing imaginary part of psi1 star plus psi2 star times del psi1 upon del x plus del psi2 upon del x. In this case, The first term, that is psi1 star del psi1 upon del x, would represent you what? It will represent you J1. The second one, psi2 star into del psi2 upon del 2, imaginary. So I think h cat upon m should also come. This would represent you J2. Now there would be another term which is h cat upon m, imaginary part of psi1 star del psi2 upon del x plus psi2 star del psi1 upon del x. Now we want to evaluate this. This will be, forget about this, just evaluate this bracket. If I'm evaluating this bracket, I'm writing it here. And if I'm evaluating this bracket, this will be h cat upon m. Let me write psi1 star. So psi1 star would be a1 e की power minus iota k. So it will be a1 e की power minus iota k1. So it will be not even k1, sorry, e की power minus iota kx. And from here, what is del psi 2 upon del x? It is minus iota k a2 e की power of minus of iota kx. Okay, and then plus what is psi 2 star? Psi 2 star is simply a2 e की power iota kx times del psi 1 upon del x. So del psi 1 upon del x will be iota k a1 e की power of iota kx. I hope it is not wrong. Okay, so overall, if I just calculate, so Jx, it is equals to J1 plus J2, that is fine. Then this bracket, I'm going to write this as plus bracket, sorry, plus a bracket, which is h cat upon m, imaginary part of, so sorry about this, imaginary part of, now just see, these constants would come A1, A2, and K. So I'll write K, A1, A2 outside. So K times A1, A2 will be outside. Now inside, what is there? Just think about that. So inside you have an iota, and then you have this e की power of 2 iota kx minus iota e की power minus 2 iota kx, which is equivalent to writing. So if I take this, if I take divide it by 2 iota, if I divide it by 2 iota simply, so I'm just writing it so that you get to know. So it is like J1 plus J2 plus K A1 A2 h cat upon m. Imaginary part of iota is here, and what this is equal to, this is equals to 2 iota sine of 2kx, and which is equal to iota. Iota will become iota square. Iota square is minus 1. So this entire entity is real. This entire entity is real. This entire entity is real. So overall, this particular bracket would go to 0. So I can say that my Jx also follows the superposition. Okay, it also follows the superposition. However, you can check that rho, that is the probability current, probability density, is not equals to rho1 plus rho. It's quite easy to see. You can see on your own also that if I'm writing psi as psi1 star into psi2, psi star into psi, that is psi1 star plus psi2 star times psi1 plus psi2. So you will get this psi1 mod whole square. This is fine. You will get psi2 mod whole square, but you will also get this cross term. And you will find that this cross term is not a 0. So basically, this is your rho. Rho is equal to rho1 plus rho2 is fine, but this particular bracket will survive. This particular bracket will survive, and this particular bracket will be equals to 2 times A1, A2. I'm just writing it for you. I'm leaving it to you as an exercise. So clearly, if the two wave functions, two plane waves are superposing, and the waves are given by A1 e की power iota kx moving along x-axis and one other moving along negative x-axis, then the probability current densities will also follow this superposition. That is corresponding to this psi1 if the probability current density is J1, and corresponding to this psi2 if the probability current density is J2, then Jx can be written as J1 plus J2. However, rho cannot be written as rho1 plus rho. I hope you're able to get whatever I'm speaking. Please let me know if there is a doubt. And here I finish this lecture on revisit of wave mechanics pertaining to the discussion of probability current density. Please try to do all the questions that have come in the examination, and please let me know if you're getting stuck somewhere. Till then, take care. Bye-bye.